Please down here.
Hello, good morning. Morning. How was the exam? Smiling. There was a mistake in the solution for problem 1. So if you interpreted that, so make sure you correct yourself, or I'll make a correction in the errata that I maintained. And I have finished grading the first 4 problems. I was hoping to finish it by today, but I could not. So hopefully very soon, probably tonight, but surely before the next class. Probably sometime later in the evening. So anything you want to mention? Anyone? I got a couple of feedback on problem 4, so maybe I should point that out. So problem, I think it was problem 4, right? Where there are concentric shells. And that's a negative charge. Electric field starts from the positive charge and ends in the negative charge. So that, I think most of you got that clear. That's very good. But then that leads to a confusion. There could also be electric field lines starting from infinity and coming down to negative charges. One might argue that there are field lines coming all the way from infinity to there. That's why you have to use Gauss's law. If you put a surface around this, total charge is 0, electric field cannot be there. The electric field is 0 outside. That's because the total charge is 0 inside. So concentric spheres does not do the job. There was, I noticed some confusion that these were 2 shells. That's something that I noticed, but I think that has to do with the word concentric being used there, probably. In those kind of situations, whenever you don't understand the meaning of a word, ask me. That's the only way I think I can settle that. During the exam, if you don't understand a word, please ask me. That's the best I can suggest. If words become confusing, right? And certain things, context also helps, I suppose. That's the best I can suggest. Yeah. Yes,
But
please.
you're saying electric field is zero outside.
Even the outside, because remember Gauss's law, which is suppose this was a field, you would say, and Gauss's law would say that E dotted with the A is equal to charge enclosed over. Because there are positive charge here, that's a positive charge Q, that is a negative charge Q here. Together, that's zero. These two together, zero makes that equal to zero. If this is equal to zero and the area is fixed, so the only way you can argue that is that electric field is equal to zero. You cannot argue that from identity because now there is a charge. So inside this surface there is a charge, positive. So electric field is there inside. Again, you put another surface here, charge becomes zero. Here, electric field is zero here. Field is zero here. In between it's fine. So the overall it looks like this. If you argue that there is an electric field coming inwards, that's understandable, but with a little more thought, you could have done that. So it's not very bad if you got that electric field lines to be non-zero outside. So I think the way I was grading is that if you drew the lines coming from outside, I think I still gave some 2 or 3 points. I don't know, remember exactly how it is. So if you got completely correct, that's okay, but then you lost little points if you drew the lines coming from outside. But if you really interpreted that question in a different way, then yeah, you did lose points. But most of you got at least going from positive to negative charge. I think most of you got that right. So that's a good thing. Yeah. Okay. Any other comments or questions? Okay. So there's a homework screen that's been posted. September 7. Tuesday, so we have lectures today and Thursday, and you should be able to finish it by Tuesday. The next midterm, there will be more homeworks. The plan for the homework got disturbed a little because we had a review session, which I typically do not have, and since it's at 1 hour and 15 minutes, a review session really takes away too many lectures. But I'll try to maybe rush a little if it is possible. So if you feel like I'm rushing, ask questions so that can slow down. That's one way you can control. So, October 18. That's relatively far, so you don't have to worry now. Okay. Most of what we have done in the last, I think we have finished 4 weeks of classes, is introduce the idea of an electric force and the associated idea of force per unit charge. But we said that's a lot more physics associated with that. That comes into play when we have covered a little more, bit more to be able to appreciate that. And that's the idea of electric field. So electric force, which acts on charges, is an electric charge, electric force, and electric field, which is force per unit charge. But earlier, if you recall your concepts you learned in the first part of the whole course, which is the mechanics, you must remember that for every force, you associate a work done by a force, and under very special conditions, very rarely, extremely rarely, you have a potential energy associated with a force. You do not come across very often that you associate a potential energy associated with a force, and those are called conservative forces. And there are how many conservative forces you have seen as of now? Anyone? Or list the conservative forces you're aware of? Okay, come across anyone? Feel free. Yes, please. Yes, gravity. You talk about gravitational potential energy. Every time there is a conservative force, you talk about a potential energy, gravitational potential energy. Right? Which other force have you seen which has a potential energy associated with it? Yes, please, man. Yeah, spring also is a force that involves a potential energy. So you don't give it a name because in nature we don't really have that as a fundamental force, so it's not given any special name for the potential energy, but correct. It is spring constant times the length that you extended. Any other? Torque, no, the torque force or it's an angular force, no. In fact, you've not seen any other potential energy in the semester. You have seen a lot of forces, but not many potential energies. You can talk about work done by forces, but not many conservative forces, and they are very rare. In fact, in a sense, you can say that there are only 4 conservative forces, and those are the 4 fundamental forces. If you find a conservative force, that means your fundamental understanding of that force is very good. Then you can do a lot of predictions out of it. Most of the forces that we talk about, they're not fundamental. That means that you cannot associate a potential energy associated with it, which also means that they're very empirical, like friction, for example. When you say friction is going to be the friction times the normal force, that's a model. It works to a certain extent, but if you do a very precise experiment, most probably that's not perfectly correct. It might be correct to 1 significant digit, but not probably correct to 3 significant digits. But electricity and magnetism that we are studying, that's accurate to 13 significant digits, and most probably can go pretty high significant digits. So in that sense, it's a fundamental force that we know. Our understanding of the force is extremely good, and so we are studying an electric we're studying electric force, and it is a conservative force, which I will do a very quick review on. What a conservative force is, what the work done, and what's the potential energy. We will spend some time, and all of us should have expectations that all of us have done some. Spend some time on that. So I'll spend a few minutes on that, reminding also what work done is and what potential energy is. Then we associate an electric potential energy, in principle electrostatic potential energy, and we talk about electric potential, we talk about energy per unit charge. We define force per unit charge, that was electric field. We will similarly talk about energy per unit charge, that will be the electric potential. That will be a big important concept. That's what we see as voltage when you think of 110 or 120 volts on the wall. That's basically the energy per unit charge. And from that point on, we will be able to talk about devices. We will be able to talk about electrical devices which we can use to build gadgets, right? And that played historically, I could say, a very important role from about 200 years back. The way we are sort of living in a revolution which is called a digital revolution. Internet is really playing a significant role. The technology is changing very quickly. There was a very similar revolution in about 1810, 1820, when they really discovered electricity and magnetism, and they could really come up with new gadgets every other year, and that played an important role. So we are kind of studying those things. It may not come out as applicable as they were in those days, because now that we have refined it a lot. Like a course like this will give you a fundamental idea, but probably you cannot fix your car or fix your electrical gadget very easily because it involves a lot more engineering, a lot more trial and error has gone through. But nevertheless, this is necessary for understanding the basics of whatever is going on there. So that's the idea. So let's introduce the idea of work done by a force. Let's review work done by a force. Force F. You say the size like unit of energy is the size of energy. The idea is that an object goes from initial to final point. So it's our initial. That's our final. And somewhere along the path, you define a small element of displacement. Let's call it dr or d. I think we might have used dl. Sometimes it's used dr or dl. That's a tiny displacement along the path. And the work done is like you get the dot product of the force with every tiny element along which it is moved. And the idea is it helping in the motion or is it resisting in the motion? If it is in the direction, is a force here, that would be a force acting on this particle down here. Like it might be changing as the particle is moving at this point, it might be making this angle, at this point, it might be making another angle. So pretending that we know the force at every point, at each point you ask whether it is helping or resisting the motion, add or up. So you are going from our initial to our final. And that's called the work done. Is that a precise enough formula? Something missing in that? You remember from the last semester or from your definitions of work done? The definition I've given, there's an ambiguity in this way of saying it. What is the ambiguity? To go from point R initial to R final, there are many ways of reaching there. Like geometrically speaking, the particle can go in different ways. So I have specified the work done along a path. Necessary that I specify that path. Typically, you say it is the path taken by the particle itself, but otherwise you have specified that path, and then that's a well-defined quantity. And sometimes it happens, very rarely, that this is independent of the path. I just introduced the idea that it is ambiguous if you do not specify the path. If by any chance it is independent of the path, very rarely that happens. Gravity is a classic example. In that case, if the work done is independent of the path, then two things happen. What is, of course, it is path independent, that the change in energy depends only on the initial and final points. That means to say that you can start from here and very dramatically speaking, you can go all the way to another galaxy and come back and still your gravitational potential energy, the difference would be in fact zero if you come back home to the same point. So anywhere, whichever galaxy you go, it will always come out to be zero. So whatever is the work done in one way, it will cancel out the other way, irrespective of which path you take. So that's a very big constraint you put in. What you're saying is that the function representing that potential energy is already decided, like based on where the masses are, that is completely decided. So if that is independent of the path, then F is conservative. And you can associate a potential energy to that, so it's as a final minus initial, and then you can associate a potential energy, change in potential energy is equal to minus of that. Minus is just a notational feature, you want to connect it with kinetic energy, and that is the reason why you put a minus there. So basically, the idea of potential energy, if it goes there, the potential energy is negative of the force, force of the work done by the force. So that's the very short, very quick summary of conservative forces, and the electrostatic force that we are talking about, K Coulomb's law, Q1 Q2 over R square, with a constant K sitting in front, which is basically mostly based on units, and that's a conservative force. One can do this integral, and one can learn that this is actually a conservative force. It is path independent, and that means that you can define a potential energy associated with it. Energy is the work done by a force, in fact, negative work done by a force. So electric potential energy is defined as the electric force F dotted with dl and negative of that. So electric potential energy or change in electric potential energy will be defined as negative of let's say, let me write dl first of dr this time. That's dr dotted with K force was R hat. So let me write the R hat first. R hat, sorry. K Q1 Q2 over R squared. And again, R initial to R final. Remember, this is a dot product. Dot product between two vectors is equal to 0 whenever it is these two quantities are perpendicular. Two vectors are perpendicular. The dot product is 0. So let's try to work this out for a point charge. So this is electrostatic force due to a point charge acting on another one. So let's say that is a positive charge here. And its electric field lines, remember, is the representation of what force will act on a charge. So that's your electric field lines. This means that if I place another charge Q2 here, so that's Q1. If I place Q2 here, that could be down here, it will experience a force radially outward, and that amount of force is by Coulomb's law, this quantity, right? That's what we are talking about. Notice if this is my R initial, and if I want to go to another point, R final here, that could be my R final. I can break this path in many ways. It is path independent, so I can break it in many ways I want to. So I will choose my path to be mostly along the radial line and rest of it on a circular arc. Well, let me first go this way. I have a choice to choose my path. It is path independent. I go this way. And then go this way. That's my path. Path independent, I go anywhere I want to. You might want to go all the way radially out there. And then come along that direction. That's also perfectly fine. Or you can take a diagonal line, straight line. That's also perfectly fine. Pick your choice. But these two, the first two that I mentioned, have an advantage that most of it is going to get contribution from the radial. Now let's talk about. Let's break this into 1 and 2, right? So this is 1 and 2. So let's talk about so delta U along path 1. So this is the change in energy you get by going from our initial, keep the radius the same, and you reach this point. So let's say you so what could I call that? A point B maybe. That's point A, point B, that's point C. Let's go from point A to point B maybe. What is the change in potential energy for that particular path? Anyone? It's 0. That's correct answer because it is perpendicular. This path DL is perpendicular to the force. Electric field line is radial. This is tangential. At every point along this path, the force and the path itself, or the displacement that the object will go along that path is perpendicular, and that is 0. Dot product of two vectors is 0 if it is 90 degrees. So that's equal to 0. Because F dot is the DL on that path is equal to 0, this is 90 degrees. And that plays an important role in all of these discussions, or in fact, whenever it is path independent, this argument comes in that whenever you go perpendicular to the direction of the force, you do not do any work, or there is no change in potential energy. Think of a classic example of a mass you carry. So I have let's say I have this chalk I'm carrying in my hand, and I move with this chalk along this along the path, but I'm keeping the height exactly the same. And you ask, not the work done by me, that's too complicated, but what's the work done by the gravitational force? And that's a change in potential energy. Not the work done by me, that's too complicated. We have calories and how my muscles work. That we don't understand that very much, but we do understand how gravitational force does work on it, and that is 0 because there is no change in height. Right, but force is acting downward, displacement is horizontal, so there is a 90-degree angle there, that's 0. Immediately 0, there is no work done by gravitational force. Whenever you go perpendicular, when you go on a stack, every time you go horizontal, there is no change in potential energy. Only when you go vertical on a stack, there is a change in potential energy. Doesn't mean you're not doing work. You work horizontally for a long time, you do a lot of work, but that's not what we're talking about. We're talking about the work done by the gravitational force. That's a different concept, right? Not the work done by you. Sometimes it is the same. If you say the energy is not lost in anywhere else, then you say that whatever was lost from, or whatever energy was gained or lost by potential energy due to gravity is the same amount of work done by you. But in general, that's not true. So in that way of saying this is equal to 0, so all the contribution comes from here to there. Only when you go radially out in this scenario, it works, or the gravitational force does any work, so there is a contribution to potential energy, and the change in potential energy then is the total change in potential energy, because this is 0, It's simply going from our initial to our final. And this time I don't have to talk about a vector, which is a magnitude term. It doesn't matter which point on the surface I reach. As far as I reach here or here, anywhere on this sphere versus that sphere, go from one sphere to the other, it's the same work done by the electric force, not by who is doing the work, by the electric force. It is the same amount because every time you go along the surface, you do not do any electric work. So this vector, notice the difference. This vector has become a scalar now. This is no more vector. We just talked about the radius. dr, if we go from point B to point C, that is purely radial. That's dr times r hat. Dotted with r hat itself, and take q1, k2 over r square. We're talking about this quantity here. First, I have used that point A to point B. The work done by electric force is 0. From point B to point C, we are going radially outward. Radially outward, the r is the length itself times r hat, and that cancels out in the sense that the dot product of these two is equal to 1. It's not really cancellation. The contribution is unity from that. And that leads us to a simple integral. So that's equal to minus k q1 q2. That's not, the integral is over r. q1 and q2 does not change. K is a constant, and that's a integral we know how to work. That's dr r squared. Here, if you feel more comfortable using x, replace it with x, like dx over x squared. But now by now we could start changing variables and be able to integrate with any quantity. Remember your integral formula, the x over times x raised to n. That's equal to x raised to n plus 1 over n plus 1. So we are doing dr over r squared. R over r squared, that's the same as r raised to minus 2. So that's r raised to minus 2 plus 1 divided by minus 2 plus 1. That's minus 2 plus 1 is minus 1. So that's minus of 1 over r. That's minus 2 plus 1 is minus 1. Put it in the denominator again. And that's minus 1 over r. The minus and the minus 1 over r cancel, and I have to take the limits. So that's equal to k q1 q2 over r evaluated between our final and our initial. That's a change in potential energy to go from any point close to the sphere to another point close to a sphere. Let me write this as u final minus u initial. And this, when you evaluate, this is k q1 q2 over our final minus k q1 q2 over initial. That lets us identify that the potential energy is actually one of this, and we evaluate at two different points. So the key things you want to take home out of all this. So I motivated you that if there is an electric force, which is what Coulomb told us, then there must be an associated potential energy, and the electric potential energy is is U is equal to K Q1 Q2 over R. The only difference being earlier force was R squared and there was a vector associated with it. It was a vector quantity. Energy is a scalar quantity, sometimes a lot more easier to work with, but at the same time, little more geometric in nature. So a lot of intuition is needed. Force is a lot more intuitive and algebraic, less amount of geometry in that if you think of the intuition and mechanical way of evaluation. So when you're really working out a problem, force helps a lot, but when you're trying to imagine at a global level, bird's eye view of the whole problem, then sometimes energy principles are much more useful. Often, not necessarily, sometimes, like notice that if I have a constant here, this is okay. If I change my definition by add a constant to this, that will not contribute because they cancel out. So any definition of potential energy will always be off by a constant. When you talk about the gravitational potential energy, we usually say that the potential energy is zero on the surface of Earth, right? But that's not necessary. You can move it anywhere else and that still works. So the definition of potential energy is off by a constant. In that sense, it is not really measurable, because how does the experiment know that which origin you have chosen? So in that sense, it is not really truly a measurable quantity. It is always the force that is measured, and one would argue that energy is not measured. Having said that, that is how it is insufficient to work with most of the time you're doing engineering, but in a more advanced setup, it really bothers because energy can interact with gravity. Remember, Einstein said that E is equal to mc squared. That's a more advanced topic. It said that energy is equal to mass times c squared. So anything that has energy, what it says is that it behaves like a mass. Photon does not have a mass, but it can get attracted to a very huge planet. It bends light. Light can be bent. That means that energy does get attracted to a planet, and then it becomes much more physical. So the question arises as if you put a constant there, does that constant get attracted to gravity or not? Like we say that that is not important because change in energy is what is measurable, but that constant probably goes into Einstein's equation, and then the question remains that does that get attracted to that or not? And that's not a very easily solved problem. As of today, you might have heard of what is cosmological constant control, and those are all very loosely associated with this constant. It looks a very innocent constant there, or I can add a constant there, and they subtract out, but that has a bigger issue. That is, that's a constant, but gravity you cannot ignore that. Here you can ignore because force depends on the change in energy. But when it in a gravitational setup, every energy has to interact with gravity. Having said that, with that caveat, we will not worry about that constant because it is going to be cancelled out. But just for keeping this intact, let's do this. We can have a choice, right? So a choice. If that constant really bothers you, have a choice that we are going to say that potential energy at infinity. So F R tends to infinity. So when the charges are very far apart, you choose your energy to be zero. So U is equal to zero. That's a choice. I could have said that it's not zero there, that is 56 joules there. 42 joules there, and that would have been perfectly fine. Nothing would have changed because that would have cancelled the two quantities in here, and nothing would have changed. For our purposes, what we want is this quantity here. This is what will play an important role in every setup. If you do not want the baggage of integration with you, work with this formula and to take you along distance. So as far as concept goes, that equation has a lot of concepts, or most of the concept is in there, and integrated in the tool where you can actually do a lot of stuff with that formula. Okay, so that's electrical potential energy. Like electric field. Do an example, maybe before I go to electric. Another concept of example. Let's say I talked about a single charge here. We could have multiple charges. So let's say we have, so let's say that is Q1. Again, it's square. Positive. Negative. Two. So, oh, I meant negative here, sorry. So diagonally opposite, you have the same kind of charge. Let's say the magnitude wise, all of them are the same, just for convenience. Yeah, let's keep that all the same. It's, in this case, we are not working with forces, so it is often much more easier, so you can even work with non-constant, and the algebraic equations are not that bad to deal with. By not that bad, I mean even in an exam in 5 minutes to 10 minutes setup time that you have, you can work on it. In your homework, I expect that you should be able to do long calculations. Okay. So that's your 4 charges. All the magnitudes are the same. Let's say what is the potential energy of a charge Q5 here, so that's positive charge of fission interaction energy of 5 with 1, 2, 3, and 4. Notice that I'm only talking about 5 interacting with 1, 2, 3, and 4. 1 and 2 interact. I'm not interested in that. I'm only interested in 5 interacting with 1, 5 interacting with 2, 5 interacting with 3, and 5 interacting with 4. There is interaction between those two, but that means to say that I'm keeping these 4 static. This is the stack charge, if you want. 5 is a charge that we're talking about, and it's the interaction energy of that we are going to discuss. So in that sense, so U is equal to when it is at the center. So let's say this is C. So C stands for center of the square. Is equal to, can interact with each one of them. So it will be U51 plus U52 plus U53 plus U54. This interacts with this interacts with that, and so on. And each, let's say this is length L, and this is a square, so that decides everything else. All the other distances are decided by your length L. This is equal to K times all are same charges, so let's say Q. So this is Q5 minus Q1, Q squared divided by both are positive charges and divided by, notice R here. R is the distance between 1 and 5. I'm interested in this distance now, 1 and 5. This is L. Let's say this is X, but this is 90 degrees. If it's a square, that makes it 90 degrees. 2 times X squared. So 2 times X squared is equal to L squared. That makes X is equal to L over root 2. Sometimes we are interested in the total diagonal, so that's 2 times that length, and that becomes root 2 times L, because 2 times root 2 is equal to root 2 itself. So that's equal to L over root 2 then. And both are positive, so that's a positive quantity here. Its magnitude is the same, but one is positive, the other is positive, that's positive kg squared over L over root 2. The next one, 2 and 5, one is positive, one is negative, so that makes it a negative. So that's k times q squared. Numerator decides the sign in the front. In the denominator, there is a distance r that goes up. It's the same distance again. If it's a square, these distances are all the same, and that's equal to L over root 2. And of course, they cancel out, right? And that's because one is positive, one is negative. They are equidistant from the two charges. They can energy-wise, they cancel out. 5.3 now is again plus k2 squared over L over root 2, and again 5.4 is negative. And that's equal to 0. And so the energy, potential energy associated with this charge is equal to 0. If the energy is equal to 0, does that mean that the charge is stable there, or will the charge stay the same? What does the system usually try to do? Try to? Yes. Yes, it will always try to attain minimum energy. The system always try to attain a minimum energy, and 0 is not necessarily minimum. That could be another point here which has a negative energy, and it will try to go there. If you want to simply analyze quantities of physics associated with energy alone, try to have a mental picture of what is the energy at each point. This is equal to 0. If you have the ability to interpret, if this is by any chance a closer point has a negative energy below 0, then it will try to go there. And force is just a manifestation of that process. Nature is trying to minimize energy, and we interpret it as a force acting on it, because in that direction there is a motion, so there is a force. So we interpret it as a force, but energy or nature in many ways is only trying to minimize its energy. So we have to talk about change in energy. So this doesn't really help. Okay, energy is equal to 0. But if you want to do anything more interesting, you want to talk about change in energy, preferably change in energy in a very closely related point. That brings in the calculus. It is a change in energy. That's what we will do in the next class. We will define the force as change in energy with a coordinate. As you move a little bit, what is the change in energy, and that decides where the particle will go. But we will not bring calculus here today. Let's just talk about what is the change in potential energy when this goes from here to there. A significantly larger displacement, easier to calculate, but at least we will be able to tell, is it preferable for this, or will the charge Q5 is let go, is there a chance that it can run into this point? So algebraically, it is easier when you pick a point somewhere down here and or let's make it even better. Let's take it all the way to infinity. So let's take charge Q5 all the way to infinity. No, change my mind. Sorry. Let's keep it here. I think that will bring in more questions than answers. Okay, so let's move the charge here. So we are moving it here. So that's your initial point now, and that's my final point. So this is my initial point. You see how this is maybe this was C, right? So I can define this as B, point D. And do the same calculation again. So again, UD this time is equal to U51 plus U52, right? Prime this time because it is moved. U53 prime plus U54 prime. A new energy is associated with this, and this time I won't bother to calculate the distances. It is clear that this length here will be exactly the same as this length for a square. And if I'm at a point exactly at the center of the side of the square, these two distances are exactly the same. Q1 times Q5, Q2 times Q5 is exactly the same. One is positive, one is negative, they cancel out. And the same thing happens here. Right? The positive or negative quantity here, positive quantity here, again cancel out, and that's again equal to 0. Okay. I said that if the change in energy is finite, that means to say that if there was a negative energy, then I would have argued that it really goes to there, but that didn't help me very much because at this point again it is 0. So if I were going along this line, for example, so you can argue that you have the potential energy change or U itself. Right? This is along Y. That's my Y. Just for analysis purposes, if I were to argue what is my change in energy there, and what I argued that at point C, which is right at the center of that, so this is point C, and somewhere on the negative Y, that's my D. Same thing happens to a point somewhere here, and that is D prime. Let me call that D prime. All these points, energy is 0. That's 0. That is 0. There's one more point you can say it is 0, and that is when you go very far away, it is again 0 because at that point the distances are very large. So that's also 0. So there are 1, 2, 3, 4, 5 points you got where this is 0. And that's equal to R0. And now if you have to fit a function from in this, you can argue that the possibilities are that this has to go through here. So this could be one possibility. Or it could even be the other way. And change in energy is force. So the slope in an energy curve is a force, and you can decide what will be the force acting onto that. We will do this analysis in more detail in the next lecture, but here what will be interesting is that we will just restrict ourselves to what is the change in energy between 2 points. So we'll restrict to that, and you will be able to do a lot of homeworks today, I think half of the homework you should be able to do this way. But I want to introduce one more concept which will really help you a lot. Any questions at this stage? So when we introduced the idea of force, we had an associated concept called the electric field, which was force per unit charge. Same thing here, if there is a force per unit charge, energy is the concept associated with force. Define an idea called energy per unit charge. Whatever is the expression for Q1, Q2, remove the charge Q1, that becomes the energy per unit charge, and that we will define as the electric potential. So let me define that. Now this, in the beginning, or it doesn't, it's not very confusing once you accept that is a very close definition. But in the beginning, if I strike or that, this is so close to the other definition that we already said, right? So U will be electric potential energy. And V would be simply electric potential. Vocabulary wise, very closely related, but it's like a force and electric field. One is, so very broadly speaking, V is U over Q. And pay close attention to V, that's the concept you want to pick up, because all the electrical quantities that you see around, when you say 9-volt battery, that's the V, electric potential. If you want to talk about energy, you simply multiply by charge, and then you get potential electric energy associated with it. So keep close attention to that if you want to associate with the devices that you have around. But electric potential definition is change in V is going to be defined as change in potential energy divided by the charge Q. One of the charges, you remove it out, and notice that whenever you talk about energy, you have two charges. Right? By construction, it is the interaction energy between two charges. You remove one of the charge, and then you say, oh, what do you mean by energy there? Then it is an electric potential in the sense that if you keep a charge there, what is going to be the energy associated with that? Exactly like electric field, it is not the force, but that is the force that a test charge would experience if you were keeping a charge there. So in that sense, change in V is equal to minus of force started with the L, our initial to our final. Path is in general there could be a path, but that's not there. It's a conservative force. You don't need the path. Right? That should have been a path dependent on there, but it's not because it's a conservative force. So that's gone. The electric force I'm talking about. So that's equal to Q times E. And I have to divide by the charge Q, or divide it out by Q. So Q cancels out, and what is left out is the definition of electric potential, change in electric potential. And that's minus our initial vector, our final E dot at the out. It's always the change in potential. If you remember, if you have, even if you have a very simple experience with electricity, it's simply because we plug in things into the wall outlet, you might always think about ground. Like often you say where slippers, whenever you're working with electric quantities, that's because the ground acts like a very important point there, that's the reference point, that's a constant. I talked about a constant there, ground is a constant. There's a change in potential that I've always talked about. When you say it's 110 or 120 volts, it's with respect to the ground. It's a change in potential with respect to the ground. So that change is important, and that's what this quantity is. And if this is the electric field, it's just the charge you have to replace or pull out, and the electric potential goes exactly the same way that we talked about earlier. And V comes out to be, again, with reference to at infinity, you can choose that to be 0, and you simply take Q1 or K2 over R. You first strip out the length in the denominator that you got gave you the energy. Now you take away the charge from the numerator, that gives electric potential. So that gives you 4 quantities that are interrelated. And let me draw a quick diagram. It often is useful. So we first introduce the idea of force between 2 point charges. That's the Coulomb's law. Then we introduce the idea of electric field. They were closely related to each other. And now we have introduced the idea of energy, the electric potential energy. And we then said there is an electric potential which is associated with this. And they are all interrelated. There's only one concept you need. You can work the whole of whatever is needed with that. But since we have such a good understanding of this force, we can see it from 4 different perspectives. One is the force and the electric field, which we said is connected by the equation. Force is equal to Q times electric field. Right, that's your connection. And if you're talking about point charges, this is, let me start with the force. That's equal to K Q1 Q2 divided by R squared, and then R hat. That tells you what the direction is, symbolic representation of that force. And these two are connected. So this is K Q1, so let's say this is Q2. This is Q1 over R squared, and let's say R hat. You remove a charge Q2 and you're left out with electric field. That's all in charge being divided, but then force and energy are related. Any force and work done is related. In this case, you can define a potential energy that gives a connection, and that's connection is change in potential energy is minus of force started with the out. So let's say A to B. By that I mean we write that more precisely. Initials are fine. The same expression that we wrote. Hope that's clear. Turn your head. Yeah, okay. For energy, this is K Q1 Q2 over R. It is misleading to think that it is just multiplied by R. It is not algebraic that came out of an integral. It came out of an integral, we got lucky that no coefficients came out. If it was any other power, we could have got another coefficient in there. Same thing in here. Let me not try to write it like that. Let's see if this is like it. Okay, suppose that's minus of our initial final E dot of the P dot. And this leads to equation this is K Q1 over R. That. And then we ask, oh, that must be a connection here. If there is all these connections, there must be a connection there, which we pointed out is divided by Q. I raised it here, and the connection is U, or change in U. Change in U is equal to Q times change in V. All this is for spherical configurations, right? I said we'll talk about spherical configurations and planar configurations. Planar configurations are significantly easier. And the big advantage is there is no integration needed. There is no 1 over R squared. This is just a constant, right? Electric field is simply constant. If you don't talk about what exactly it is like when you work with gravity, it is 9.8 meters per second squared. There was a reason why we worked with all gravitational forces in the first part of in the introductory level. That's because it's a constant, very easy to work with. Then when you go outside the surface or little away from the surface of Earth, like if you're on an interactive space station, then the distances are large enough, and then you have to worry about the distance dependence in them. So let's now get close to the surface and let's say uniform electric field and how these things work out. So planar configurations. And the big advantage is that E is constant. What do you imagine? Planar configurations. Planar configuration diagram would be this. Your electric field going down. Think of gravity, gravitational field pointing downwards. That's your electric field. How would you generate this electric field? Positive charges here, negative charges at the bottom. That's here. If you have a positive charge Q, it tends to fall in the direction of the electric field. Or better word is a positive charge flows along the electric field, a negative charge goes against the electric field. A mass left on its own, it follows the path of the gravitational field. That's a uniform field, and this should also be imagined as like when we talk about a surface, positive charge. Same thing here. Notice as you get closer and closer to the surface of this chart, there are more lines here, and it's another way of looking at it is that you make this bigger and bigger, these lines get more and more aligned with respect to each other. As you get closer and closer, there are more and more lines here. And very close, they are all parallel. So this is nothing but an approximation of a sphere. A sphere of very large radius is pretty much a plane only in that small angular region, not everywhere. A sphere is a sphere, and you're not going to take the geometry, but if you restrict your movement to a small angle within, let's say, if you are always think you're holiday or if you are in a city and you don't go around anywhere beyond that city, then you're confined to that region, and for many purposes, your region is flat. Unless you go very far away, that angular dependence doesn't come in. In that case, electric field is a constant. Important point is that E is equal to a constant. Gravitational field is a constant on the surface of Earth, 9.8 meters per second square. E is a constant which depends only on the charge density of that plate. With that in mind, then all this we should be able to write, right? With the expressions that we learned today, new expressions that we learned, these two, right? And these are already known, but we should be able to talk about the same quantities. F E, this is a constant. So force is U times a constant. Nothing has to do, because if this is, for example, if this was 9.8 meters per second square or Newton per coulomb, the units are different. You just multiply by the charge and you know the force that will act on. What about the energy? Now, if it's a constant, this should be very simple. This is an integral, force dotted with a distance. So Q times E dotted with a distance. So potential energy, U is simply Q times E times, let's call it the height X. Remember your mgh, m in electricity and gravity, replace the charge with mass, E with G, and your gravitational potential energy was mgh. Here it is Q E H. Right? So instead of having 1 over R dependent, in gravity also you have it here on, because close to the plate, because the case here, parallel plates, in between the parallel plates, the change in potential energy is this. And if you want to go from this point to that point, you go straight up there, there is no potential energy difference perpendicular to the electric field line. Like these fields act like gravity. Go in here, and you can define a potential also now, right? Electric potential, and that will be, you just have to remove the Q now, that's equal to E times H. And that becomes conceptually very easy to think of. Right? Whenever you want to think of what is electric potential, think of parallel plates, and you ask for a positive charge, it wants to go to a lower energy. You want to ask, is it lower in energy here or there? Often force considerations help here. Positive charges that repel, but energy considerations let you ask, is the potential energy here lower or here? Just because it is going to go this side, you know that the potential energy will be lower at this point compared to that. And in the same argument, electric potential will be lower at that point relative to the higher point. It depends on whether it's a positive charge or a negative charge. We'll develop these concepts more next time, and very soon talk about electrical devices. Thank you.